Hello everyone. Wait, let me fix something real quick. Do I need to fix it? Maybe not. Alright, anyway, welcome to today's stream, and I will be, I don't know, doing a revision, a summary of the chemistry topic, Halogen Derivatives. Alright, give me a sec, let me fix this real quick. Alright, here we go. Anyway, this is A-levels chemistry, and I'm just gonna try and do a quick revision for those who need it. Probably just me. I'll probably watch this what's it called? Stream again to revise. I'm starting on chapter 15 because a week from now I'll have my exam, and this will be part of it. Chapter 1 isn't, so there will be no point for me to do that stream now. So we'll just start with chapter 15. I'll probably do all the chapters when I have the time, but let's just start with 15. Also, I don't think they are numbered according to any international standard. It's probably just for the ease of studying. So maybe halogen derivatives, or if it's even called that in whichever school you're studying, may not be chapter 15 at all, but this is how my school labeled it. So let's get started. So we'll start off with a very quick summary of halogen derivatives. There's 4 main points really, or 5 I think, yeah, 5. Alright, so number 1 is preparation. You need to know how to prepare. Actually no, I should probably explain what halogen derivatives are. Give me a second, let me get my notes. Alright, halogen derivatives are halogen containing organic compounds, and their molecules contain the CX bond, where X is fluorine, chlorine, bromine, or iodine. Now, organic compounds. How do I explain organic compounds? I guess organic compounds contain... should I? Well, I mean, if you're studying halogen derivatives, you surely know what a organic compound is, right? Actually, wait, let me just Google it real quick to tell you what the definition of halogen compounds are. Not halogen compounds, organic compounds. Organic compounds that contain carbon. Alright, here we go. Not halogen. What's it called? Organic compounds are compounds that contain the carbon-hydrogen bond. So, you know your what's it called? Your methane. Okay, you know what? Let me share my desk. Oh, look, that's me. So, alright, here we go. So, organic compounds are those that contain, can you guys see that? Yeah, I think so. Contains the CH bond. So that's the definition of organic compound. Well, for halogen derivatives, are how do I spell organic? Organic compounds with CX bond, where should still face on. I guess we're just right. Where X equals to fluorine, chlorine, bromine, or iodine. Alright, here we go. So this is what an organic compound is, and this is what a halogen derivative is. So okay, so let's go back to our computer. Now, let's see, halogen derivatives examples. Yeah, I guess I can show you some examples. Also, let me try and center my screen, the laptop screen. If I move it here. If I zoom it in a little bit, 100%. Yeah, this is much better. Okay, lock. Maybe a little bit too, actually. Alright, this looks much better, right? Okay, so let's go back to the paper. So some halogen compounds are examples, CH3Cl, or is this CClH3? Well, I guess it doesn't matter, but this would look like this. How is it? So this would be a halogen compound. Another possible halogen compound would be something like this. This would be what is it? Phenol. Chlorobenzene. I think it's called chlorobenzene. I hope I'm not wrong. Chlorobenzene. Anyway, this is a skeletal structure. In case you don't know, this corner is an X, and it's an X. It's a carbon atom. Carbon atom, carbon atom. So they are all carbon atoms. Actually, let me draw it out like this, right? So Cl, so this is a carbon here with a double bond to another carbon here and a single bond to another carbon here, and there will be a what's it called, hydrogen here. So if I draw it out even more clearly, it would be like this. Can you guys see that? Okay, guys can. Here, 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 Cl, H, 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 H. Oh, you guys can't see the bottom. Let me move my keyboard, move this up. So you see, this is how we usually draw it, but what this means is this, and what this means is this. What this means, and what this represents. So these three are all the same. So, I guess I'll teach you guys about skeletal formula. So this is skeletal formula. This is also a skeletal formula, but this one is more widely used because a circle is easier to draw than 3 lines, and it also represents the resonance structure of the benzene ring. That's why it's a circle. But anyway, let me tell you guys about this. So you see, each line, right, represents a carbon-carbon bond. So you see this is represented by this line, and a double line represents a carbon-carbon double bond. So you see the carbon are doubly bonded to each other. And hydrogens aren't drawn out in the skeletal structure because we assume they are there. So if you look at this, you should know that there's a carbon. It forms a double bond here, a single bond here, can still form one more bond. So you know that this is naturally a hydrogen. That's why you see, as you can tell by this more elaborate diagram. So following this, everything is the same except for this one. The hydrogen is replaced by a, what's it called, chlorine atom. So as you can see, since this is an organic compound, you see it has a CH bond with a CX bond where X equals to chlorine. So this is a halogen compound. Halogen derivative. I guess it can also be called a halogen compound. But anyway, this settles what a halogen compound is. So let's continue. Yeah, let me check my notes a little bit. Okay, so yeah, we'll move on to the preparation of halogen compounds. So as you can see by this neat summary here, the preparation of halogen derivatives can be done from three main groups of organic compounds, namely alcohols, alkenes, and alkanes. So in alcohols, there's 4 ways to make it. In alkenes, there's 1 way to make it. Actually, wait, I think there are 2 ways to make it from alkenes. Let me see. This is the more, alright, this is the summary note, this is the more detailed note. So let me just check. Alkenes, yeah, that's this one. Copy. Okay. Alright, so I'll just go through them one by one. So for preparation from alcohol, right, goes by this mechanism called nucleophilic substitution. So I guess should I explain you know, it might be difficult. Well, I guess you can just remember that it goes by this mechanism called nucleophilic substitution for alcohols. And substitution just means the swapping of an atom or a group. And nucleophilic means that that mechanism goes by a nucleophilic reaction. That sounds dumb. I guess I'll explain it in more detail here. This is alcohol, right? Let's go to alcohol. Let me go to my notes and check it a little bit. Is it here? It's right here. Okay. So, I guess I'll draw it out for you guys to see. Right. Okay. So, let me move it so I have some space here. Let's see, this is the limit. Okay. So, preparations, right? Preparation. And number 1, this is number 1. It's a alcohols. And the part 1, right? If you see, it says alcohol. Oh, by the way, R just means any carbon chain. Carbon chains can basically imagine it as an organic compound, I guess. But so what this means is this is an organic compound with the OH functional group, the hydroxyl functional group. And H just means it's hydrogen, and X is any halogen atom. So it could be, well, I say that it can be any halogen atom, but for preparation, right, iodine is too reactive, so we don't use iodine. So its X is actually just chlorine, bromine, and iodine. Oh wait, sorry, not iodine. Fluorine. Fluorine is too reactive, so fluorine isn't used for preparation. Anyway, so this is how the reaction goes. The alcohol mixed with a hydrogen halide, and you get a what's it called? Halogen derivative and water. So an example of this would be alcohol, alright, ROH, and a hydrogen halide, right? So hydrogen chloride, let's say. It could be bromide, it could be iodide, it's any of the 3, right? And then you get this, a halogen derivative, and water. So you can imagine this as, let's say, CH3, CH2, OH. Then this would be CH3, CH2, Cl. So you see the R denotes the CH3, CH2, but the R can be anything really. It can be CH3, CH3, CH2. It can be as long as you want. It just denotes a organic compound. So that's what R represents. So that's an example of the first one. The second one, you can use what's this called? Phosphorus trihalide. Phosphorus trihalide, this one. Right, so how this goes is, let me give you an example again. So I will not write out the R again. I guess wait. I guess I can still write. So you have actually let me go back to the what's it called? Computer. Let me show you this. So you need 3 alcohols and a pentatrihalide, right? So an alcohol. Let's go with this one. 3 alcohols. Sorry, CH3, CH2, OH. Actually, I guess I don't need the line. Whatever. And a pentatrihalide. So let's just go with bromine. PBr3. Solid. I'm not sure if you have to write the state symbol for all of them, but I'll just write it here just to remind you guys that the pentatrihalide has to be anhydrous because it can react with water. So you want it to be in a solid form, otherwise it will not react with the alcohol, it will just react with the water. So you get, if you go back to our thing, you get 3 halogen derivatives and what's this, hydrogen, I don't know what it's called, but you get that. So you get 3 CH3 CH2 OH plus H3 PO3. So you see, wait, this is wrong. Where's my correction tape? Here it is. Isn't it weird that you use an alcohol for reaction? You still get an alcohol. Yeah, it's supposed to be Br. You get the halogen derivative here, same as here. So this is the second one. So now for the third one, we have this. This works for, alright, you notice, right? Here I use X, here I use X, which means that it works for chlorine, bromine, and iodine. But for here I use Cl because this mainly works for Cl. It can also work for, can it work for Br2? No, it can't. It can only be used for chlorine. So this one can only be used for chlorine. So you use an alcohol and a phosphorus pentachloride. And then anhydrous condition again, because phosphorus pentachloride will react with water and you don't want that, you want it to react with the alcohol. So this is how the reaction goes. So for an example, it would be like this. See, let's use CH3, CH2, CH2, OH plus phosphorus pentachloride, anhydrous, and we'll get, what will we get? We'll get CH3, CH2, CH2, Cl plus this thing plus hydrogen fluoride. So that would be how this one would work. Can you guys see it? And then for the last one, it would just be this. The last one works for, although I write chlorine there, it also works for bromide, but it's less stable and less widely used. So it's mainly for chlorides, this one. So let's get back to the paper. It would be like CH3, CH2. I just burped. Hopefully it wasn't too disgusting. Oh, I forgot the OH functional group. OH plus SOCl2 and anhydrous yet again. I think I forgot to explain what anhydrous means. It just means dry, or yeah, it just means dry. It means there's no water, anhydrous. And when there's no water, this compound is a solid. So that's why we put a solid state symbol there. And we'll get this CH3CH2Cl plus SO2 gas plus HCl gas. Now this reaction is usually used because if you notice, right, for number 1, we get our halogen derivative, but it's in water. We have to separate them. It is, you know, troublesome, mendokusai in Japanese. And for this one, we get this and this Pretty sure they're hard to separate as well. Wait, pentachloride. Let's just try halide. Yeah, hard to separate again. This one, same thing. Difficult to separate, although the hydrogen chloride is liberated as a gas, and you'll see white fumes, so it's not that bad. But this is super easy because you see our product, right, is this thing and sulfur dichloride. Is it? What's it called? Sulfur dioxide. Sulfur dioxide and hydrogen chloride, and both of them are gas, which means after the reaction, right, these two will escape into the atmosphere, you know, just poof, disappear, and you're left with this. So this reaction, for this reaction, it's very easy to get a product we want. We don't have to spend too hard separating them. So that's why this reaction is usually favored if you want to get a chloride containing halogen derivative. Right, so that's for our preparation of alcohols. Now let's go back to this. Okay, second one is alkenes by electrophilic addition. There's addition because the compounds just get more atoms without losing any, so it's an addition. And it's electrophilic because it acts on the carbon double bond functional group, which is electron rich. That's why it's electrophilic. I think that's how it works. Anyway, let me look at my notes. Let me organize my desk a little bit. Okay. So if we were to go to the paper, right, this preparation, and this is A alcohols, now it's B alkenes. Now the first way, don't need this. It goes is, let's say you have this thing. This is ugly. Let me redraw that. Okay, so an alkene has a CC double bond, right? So there will be a H here, or H here, or whatever. There doesn't matter. And then use a hydrogen halide gas. We haven't used iodine, so let's use iodine gas, and you get this. Okay, you see how this carbon had two bonds here, right? So these 2 bonds, and these 2 bonds are these 2 bonds right here. So you see it's addition because the hydrogen and iodine is added to this compound. See, the double bond breaks to form a single bond with the hydrogen and form a single bond with the iodine. So this is how this works. Yeah, electrophilic addition. Oh yeah, I forgot to go through all the reagents and condition for each reaction, but I guess we can go through that later. I can just tell you guys later. Anyway, the second one, we use same thing, you know, alkenes, and then we use the gas just itself, not a hydrogen halide, just the gas itself. So it'll be I2 gas, and then we'll form almost the exact same thing. This is too messy. Let's just drag the arrow out over here. You get this thing. So you see, instead of a H here, you see if you use a halide, you use a hydrogen halide, you have a H here. But if you use the gas itself, I2, then you just add 2 iodines here. So that's how this one goes. So nope. So yeah, that was alkene and HX gas. I guess I should put the gas. Is it a gas? Oh no, it's not a gas. This is a... Sorry about that. This is not a gas. I guess you can use a gas, but it's actually dissolved in CCl4. That looks ugly. I2 in CCl4. Yeah, this is actually I2 dissolved in CCl4. It's not a gas, although I think a gas will work as well. Anyway, for the last one for the preparation is alkenes. Alkanes. And alkanes go by free radical substitution because I'm pretty sure that's the only reaction they can go through. The mechanism is kind of hard to teach now. I'll teach it when I go through alkanes. But it's basically, wait a minute. This is wrong. The equation's wrong. Should be this one. Yeah. So how this will look like on paper would be something like this. CH3, CH2, CH2, no, CH3, CH3 plus let's use bromine, and then we'll get something like this. Is that right? Yeah, this is right. So that's how it would react with alkenes. Although the problem with alkenes is that you might get more products than you want, I guess. So way you can put it, because it may not start at RBR because wait, where did I put RBR? It should be CH3 CH2Br, but it also could be CH2Br CH2Br plus, I guess, 2HPr. But then it would need 2Br2. But the thing is, with free radical substitution, right, the products are relatively unpredictable, so we avoid using alkanes to make halogen derivatives. So that's all for the preparation. Let me go through the reagents and conditions because I didn't go through them. So yeah, this is detailed notes for alkanes, which we just go through. So I guess I'll just read it aloud. The reagent would be X2 dissolved in an inert solvent like CCl4, and the condition would be UV light or sunlight or heat. So the note is that, polysubstitution may occur, like I said just now. And then, oh yeah, we have to note the stability of the carbon radicals, because the more stable carbon radical will be the major product. So that's that. For alkenes, if you only want to make add 1x per molecule for the alkene, then this is the equation. The reagent is dry gaseous hydrogen halide gas. Condition is just room temperature. If you want to add 2x per molecule, then it would be an X2 gas. Can be dissolved in an inert solvent to add 2x to your alkene to form your halogen derivative. You can also use a compound like because all this, right, can be Cl2Br2, right? But you can also add IBr. Wait, let me see. Can it not be I? I'm pretty sure it can be I. Anyway, you can use IBr to get two different X. So what this means is you get let's try it out. So you get something like, instead of an I here, right, it could also be Br. So that's what it means. So yeah, the condition is dark in the absence of ultraviolet light. This is to prevent free radical substitution from happening, because if you remember, alkenes, well, some alkenes, right, have a CH bond. No, how I say? Well, basically, if there is UV light, right, you can undergo free radical substitution. But in this reaction, we only want to use the electrophilic addition, so you do it in the absence of UV light, and room temperature is enough. And this is, if the reaction proceeds, this is what you will observe. So lastly, let's go to alcohol. Yeah, for the first equation, sometimes this is added as a catalyst. For the second equation, using phosphorus trihalide, these are the notes. Reagent conditions, there isn't much. For phosphorus pentachlorides, yeah, not much there. Well, I guess you can read this by yourself. But anyway, this is a summary. Or if you want to form each halogen derivative, you want to form a chloride derivative, bromide, iodide. These are basically our go-to, and these are the ones that we can use as well. So that's for what's it called? The preparation. So let's go to the next part. I guess it will make sense to go through the reactions, but let's go to our mechanisms, the SN1 and SN2 mechanisms first. So let me check, let's flip to my notes. SN1, SN2, let's go with SN2 first. Okay, so the SN2 mechanism. This is 3. Actually, should I go with SN1? I guess I can just flip the order here. Oh, that's not what I meant to do. Go here. Okay, 3, A, S, and 2. Okay, so these mechanisms are nucleophilic, anti-nucleophilic substitution. They're nucleophilic substitutions mechanisms. So let's go to our paper, SN2, right? Okay. Okay, SN2 mechanisms. Actually, maybe I'll write it down a little bit. There, much better. Okay, so how it works is basically you have your nucleophile, right, with the lone pair and of course a negative charge. If your nucleophile has a negative charge, then this is your halogen derivative, the CX bond. And then it would have a group here, it would have a group here, and it will have a group here. Now this can be, I don't know, an arene molecule, a hydrogen molecule, a hydrogen atom, or any organic chain, carbon chains. So how it works is the difference in electronegativity, right? So the halide will draw the electrons in the CX double bond to itself, so it will be delta minus charge, delta plus charge. So what this means that it's slightly more negative, is slightly more positive. So what would happen is the nucleophile, right, would be attracted, since it has a lone pair and it's negatively charged, it will be attracted to this positively charged carbon atom. So the lone pair, you have to draw the arrow from here to here. So you see this is a full arrow. You see full arrow means this, half arrow means this. Full arrow means a transfer of 2 electrons or lone pair, whereas half arrow means a transfer of 1 electron. So you can see the lone pair on this nucleophile is transferred to the carbon atom, so it will form a single bond. And since the carbon can't hold that many atoms, right, the electrons from it can't hold that many atoms, can't hold that many electrons. So the lone pair of electrons from the nucleophile goes to the carbon atom, and then the 2 electrons from this CX double bond will go to the halogen. So as a result, right, you will get this nucleophile C, R1, R3, R2, and your X minus ion. So you would get, this is how the mechanism proceed. And if you can see, it is an inversion of configuration. Yeah. Oh yeah, I should probably show you the transition state. Transition state is not really necessary, but I'll just show you. R2, R3, R1, X, nucleophile, delta minus, delta plus, brackets, and then the symbol. So this is the transition state. So this is what it looks like. Nucleophile is about to form a bond with the carbon, and the carbon halogen bond is about to break. So that's why it's dot 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 dot. So this is the transition, and this is the end result. This is not usually needed, but it's good to know. So the question we would ask is, why did the nucleophile attack from this side and not from, let's say, this side? Well, the reason is because nucleophile is negatively charged, and our what's it called? Our halogen is also negatively, well, it's partially negatively charged, right? Delta minus. So as we know, like charges repel, since they are both negative, right? They will both repel each other. So it's hard for nucleophile to approach the carbon atom from this side. So it will approach from this side. That's why it approached there, yeah. And as a result of this approaching, the nucleophile approaching from this side, it will be an inversion of configuration. Because, well, it's hard to explain why it's an inversion of configuration. Yeah, well, I guess it can be seen here as inverted, right? The R1 is like, oh, and then this is, it's just flip. Yeah, so I mean, how I say, okay, if you imagine that these two atoms are the same, right? Then you can see that there's actually a plane, a mirror plane here, and they are reflections of each other. But anyway, in this mechanism, what you need to note is the name of the mechanism. You need to show the delta plus on the carbon atom, the delta minus on the halogen atom. You need to show the lone pair of electrons on the nucleophile, which are these two dots right here. And then you need to show curly arrows to show flow of electrons. Right? Show the flow of electrons from nucleophile to carbon, from CX single bond to halogen. And then lastly, inverted product. Well, but the thing about inverted product is it's not always necessary all the time. You see, with the dot dash and the wedges, right? I think that's what they're called. It shows 3D configuration. But the thing is, if two groups are the same, right? Let's just say both of them are hydrogens, then this carbon would not be a chiral carbon because there is no plane of symmetry about the compound, right? Then if there's no plane of symmetry, it will not form an enantiomer, so there will not be a need to show the 3D. So you can just draw a straight line. Well, I guess you can't really draw a straight line, but there but I guess, yeah, there is no need because there will be no inversion. Yeah, so if two of them, right, R1, R2, and R3, right? If any two of them are the same, you don't have to show the inversion because it can't invert because it does not have a plane of symmetry. So that's why there's an asterisk here. So that's the SN2 mechanism. Anything to note about it? Well, the special thing is you need to note the backside attack, which is the side opposite the halogen atom. Oh yeah, I forgot about this. Factors affecting the reactivity. Okay, let's go back to this then. factors affecting reactivity, and then strength of CX on strength, just strength. And then the second one would be steric effect of R groups. Did I put my finger the wrong key? Steric effects of R group. Okay, so it's this two, right? So what this means is, if you look at this mechanism, right, it requires the breaking of the CX bond. So the thing is, if the CX bond is strong, right, it will need a lot of energy, and the reaction will proceed slowly. That's why, if the CX bond is stronger, the reaction will be slower. And the second thing is steric effects of R groups. So these are our R groups. Let's say R is very large. Maybe it's like, I don't know, CH3, CH2, CH2, something like that, right? Then it will block the approach of the nucleophile because it's too large, right? If it's too large, how do I say this? If you want to go through a doorway, right, but there's a giant there's like a stack of packages in the doorway. That stack of packages would be these R groups. If there's a lot of them, it will be hard to go through the doorway, right? So the reaction will proceed slowly. But if R's are very small, let's just say they're just hydrogen, and then so in the context, the doorway would have like, I don't know, a tiny 1 cubic centimeter package. Then that wouldn't really stop you, right? So the reaction will proceed quickly. So that's how it affects the reactivity. So one thing I forgot to talk about is, it's called SN2, right? You have to note that the S and the 2 are written normally, but the N is written as a subscript. So what this means is S stands for substitution, it's a nucleophilic substitution reaction. N stands for nucleophilic, and 2 is because there are 2 reactants in the rate determining steps. So let me check the notes. Yeah, the order of reaction, right? Rate is equals to K, R, X, and nucleophile. See, these two, the concentration, the concentration of these two are in the rate determining step. That's why it's SN2, 2 for 2 reactants in the rate determining step. So let's move on to SN1. So BSN1. So SN1 only has 1 reactant in the rate determining step, which is the, let me check, it's the halogen derivative. So how SN1 works is there are actually 2 steps, right? So step 1, you would have your halogen derivative. R5, R6. So what happens in the slow step is that, same thing, the electronegativity difference, the how do I explain this? Electronegativity difference, so the 2 electrons from the carbon halogen single bond is attracted to the X bond is removed, so there's bond fission. And this is the slow step, and this is the rate determining step. So you see there's only 1 reactant, that's why the rate equation is like this. Anyway, it's a slow step, so what happens is that it's a breaking of the bond. And what results is this. Oh, nothing. It's just X minus. Right, so this is what happens. The bond breaks. Oh, I formed the plus charge. So you get the X minus ion and this thing. And the step 2 would be the reaction involving your carbocation because it's a cation because there's a plus charge and there's a carbon there. big plus charge on the carbon. That's why it's a carbon cation. Yeah, here we go. So I should have moved this to the side. Oh well. Anyway, nucleophile. I will draw 2, but you should know that there is only one nucleophile in the actual reaction. So this is the nucleophile. This is nucleophile. Remember to draw the arrow from the lone pair to the carbocation. Anyway, note that this plus isn't a plus charge, it's just this nucleophile plus this reactant. So the thing is, it can proceed via A, where it attacks from the left side, or it can proceed via B, where it attacks from the right side. So what happens is that you'll get 2 products. By the way, this is a fast step. So if it goes by A, if it goes by B. If it goes by A, you can tell that there's a bond forming from the left side, so you get this. So you get this, and this is an inversion of configuration. Right, inversion of configuration, and if it goes by the right side, right, you get your R4, C, R5, R6, and then your nucleophile. And this is the retention of configuration. So if you can see our original molecule here, right, X is on the right side, and inversion because the new bond form is on the left side, so there's inversion. And you see if it goes by B, right, the nucleophile is still on the right side, that's why its retention is still the same. So that's for our SN2 mechanism. And the checklist for the SN2 mechanism will be the following. Number 1, of course, very important, name of the mechanism. Number 2, same thing, delta plus on C, delta minus on X. Number 3 would be to label the slow and fast steps. So, slow step, fast step. Can you guys see? Yeah, slow step, fast step. The delta plus, delta minus are right here. Number 4 would be bond breaking in step 1. Number 5 would be lone pair of electrons. Just lone pair. I think it's just the one. So you see your nucleophile, the lone pair, these 2 dots, these 2 dots. Number 6 would be curly arrows to show the flow of electron, like just now. Number 7 would be nucleophile attacking from either side. See, attacks from either side. But one thing to note is if 2 groups are the same, right? Let's say both of them are hydrogen atoms, that would be the same case as just now. There will be no inversion or retention because the carbon is not chiral, because there's no plane of symmetry. So in that case, you don't have to draw both, you only have to draw one. So yeah, nucleophile attacking from either side. I'm pretty sure it's only from if your compound has 3 different groups. Those 3 are different. I could be wrong though, so you should check with a teacher for that. Well, number 8 is just 2 products, but at this, like just now, it could only be 1 product. So just check and see how it goes. So that's for SN1. Let's go back to this SN1. Oh yeah. Then for factors affecting it, it would be almost the same, but this would not be this. It would be stability of carbocation. Stability of carbocation. So strength of CX bond as same as just now. If you go to this down, you see in the rate determining step we have to break the CX bond. So the strength of the CX bond affects the reactivity. But the second thing is the stability of the carbocation. So the formation of a alright, I guess we should talk about stability first. The stability, do I have, give me a second, let me prepare something. Okay, I guess we'll just use back the old page. So, right, if you look at a compound like this, H, X, you'll notice that it has these bonds, but if you look at another compound, right, if it forms a carbocation, right, it will look something like this, right? And then it would form something like, oh wait, there's no X there. CH3, CH3, CH3. I think either one works, but this is better because it shows the C is directly bonded to the C. But anyway, what you notice is that both of them has a plus charge. But the thing is, alkyl groups, right, CH3 or carbon chains, right, they are electron donating. So what happens is there are 3 electron donating groups, so it will make this carbon more negative. And if it's more negative, right, the positive charge is dispersed, so this is actually more stable. But if you look at this, there's no alkyl groups that are electron donating, so it is not as stable. So this is less stable than this one. This is more stable. It doesn't mean that this isn't stable, and it doesn't mean that this isn't... Oh, wait, how do I say? It doesn't mean that this is not stable. It's just that this is more stable than this, and this is less stable than this. So what happens is, because it's electron donating, right, positive charge is dispersed, it's more stable. So the activation energy of the reaction... Alright. See, this is for... Let's just call this A. Let's just call this B. So A would have a... Because it's more stable, the reaction would have a lower activation energy. So it's easier to proceed and it proceeds faster. Whereas B is less stable, it will have a higher activation energy and it will proceed slower. So that's what it... So that's why having a more stable carbocation, right, would make the reaction faster. And also this thing, right, it has 3 groups, right, that are not 3 alkyl groups. So this is actually a tertiary carbocation. Well, this one, I'm not sure there's a name for it. I guess it's just called a CH3 carbocation. But if it has something like this, this would be a primary carbocation. And then if it has 2 R groups, it would be a secondary carbocation. We can write this in short form as 1 and degree, 3 and degree, but note that this is called primary and this is called tertiary. You don't call it a 3-degree carbocation. Alright, so that's it. That's it for our mechanism. So let's see what's next. Cases for no reaction. Oh yeah, there are certain cases where... Actually, no, I guess I should compare them first. Comparison... Let's see. Oh yeah. So, now we know that the halogen derivatives, right, can proceed by either mechanism, SN1 or SN2, right? How do we know that? Which one proceeds by which one? So, let's see. Let me put a bracket. pH. Oh, what's it? pH. C. I think it's this one. So, if you remember the relative reactivity rate, relative rate of reaction for factors affecting the reactivity, right? So for SN2, right, it goes by the backside attack, and so what this means is that a CH3 acts or a primary halogen derivative, right, would have not much steric hindrance because there's only one alkyl group, or there is no alkyl group at all, so there's nothing blocking the approach from the backside. So if you were to look at this, right, yeah, if you look at this, if all these are very small, then there's nothing stopping it from approaching, then it's very easy for this reaction to occur. So primary or CH3 halogen derivatives will go by the SN2 mechanism. Right, is what this means, because there's not much steric hindrance. And as I explained just now, a primary or a CH3 carbocation is not as stable. I guess not. It's not stable, not as stable. And then it would not be it will be unstable, so it will take quite a while for it to proceed by the SN1 mechanism. So in the end, it only goes by SN2. So this kind of halogen proceeds by SN2, and when we explain it, we have to explain using steric effects and electronic effects. And now let's move on to this one. This one is a little bit more complicated, so let's go on to tertiary halogen derivatives. So you can see, right, a tertiary halogen derivative will go by SN1. Why? Because the three R groups are very sterically hindered. You go back here, you'll see that if these three are very large, right, it will be hard for a nucleophile to approach by this side. However, if you look at this, right, if these three are large, it doesn't matter, because once we break this bond, it can go by either side, and there's very little blocking in this configuration. So if it's a tertiary halogen derivative, it would be very sterically hindered, so it will not proceed by the SN2. However, if it's a tertiary halogen derivative, it's very stable. As I've said, there's three electron donating group. The carbocation is stable, lower activation energy. That's why the reaction is fast. That's why it will not go by the SN2 mechanism. It will go by the SN1. So for this specific compound, right? Well, a secondary halogen derivative can go by SN2 or SN1, and it depends. So I don't have any space, so I guess I'll just explain it. Wait, yes, let's do this. Okay, so this would be something like this. Wait, let's not try like this. Alright, let's follow this thing. Actually, let me see. Okay, so of course we have the C X bond, and we have the benzene ring, and then we have H, and then we have well, this one should be a little bit to this side, CH3. So you see, right, for this thing, it has a benzene ring. So what it actually looks like, it's like this, right? This is the benzene ring, right? And it is bonded to the carbon, and the carbon has a empty p orbital. Alright, all of this also have an empty no, they are not empty. They have a resonance, right, in their p orbital, so it will be one circle, it will be one circle. Well, you see, the thing is, since these are empty, it can the empty p orbitals of the carbon atom actually overlaps with the pi electron cloud of the benzene ring, so there will be a partial. Actually, it's not here, it's here. There will be a partial. Let's redraw this. So resonance, right? There'll be a partial double bond. Oh, partial double bond. Is it? Is it up? Yeah, it's a partial double bond. So the electron cloud, right, will overlap, and the pi electron can go here. So what this means is that when this bond breaks, right, and this is a plus charge, right, you notice that the positive charge is dispersed by the pi electron cloud, because you know the electrons, they flow from the benzene ring into the carbon atom. So this is actually stabilized. So if you look at this, it is stable because it's resonance stabilized. The pi electron cloud of the benzene ring helps stabilize the positive charge on the carbon atom. And if we go back to the diagram, you notice that there are two R groups, and they are very large, right? But this is not as large, but they are large, and they hinder the approach of the nucleophilic approach from here, right? It will not happen because these two are large, they're blocking it. So no, hindered by large phenyl ring or benzene ring. So for this case, it will proceed by the SN1 mechanism. So for secondary halogen derivatives, right, you have to actually work out whether it goes by SN1 or SN2. But for these other three types of halogen derivatives, right, you can safely assume that these two will proceed by SN2, this will proceed by SN1. So you just have to figure which one it is for this one. For secondary halogen derivatives. So anyway, now we will look at cases for no reaction, which are these two. So same thing as just now, right? If you have this, oh yeah, I forgot to talk about this. I guess I'll talk about it now. Besides the special case just now with the benzene ring, right? If this particular halogen, well, there used to be a bond here, right? But it's not here anymore because it's broken. It forms a carbocation, right? But all you need to notice is that there's a single bond, there's a double bond. This is the CC double bond, right? This two carbons to this two carbons. What you notice is that this carbocation is also stabilized by the pi electron cloud of the double bond, so it is stable. So even though it's a primary, you see, there's only one group here, right? It's a primary carbocation. It's a primary carbocation, but since it's stabilized by the pi electron cloud, it actually goes by the SN1 mechanism. Yes, this is a special case to take note. This goes by SN1 mechanism. So yes, this is this. Alright, and the cases for no reactions, right? So if you look at this would not undergo nucleophilic substitution, because if you look at it, right, resonance, right, and this is the chlorine atom. What you notice is that since there's a partial double bond, right, this bond is actually very hard to break. So there will not be any reaction. Let me check this out for easy from the notes. Right, the p orbital of the chlorine atom overlaps with the high electron cloud of the benzene ring, and this allows the lone pair of electrons from the halogen atom, right? It has a lone pair here, to delocalize into the benzene ring. So what this means that it results in a partial double bond character, right, for the CX bond here, and more energy is required to break this stronger CX bond. And as a result, the bond is strengthened and not easily broken. So if you notice any halogen atom directly bonded to a benzene ring, right, the bond will not break and there will be no reaction. And the second one would be something like this. Same thing. The bond will not break because, well, let me draw it out. Carbon, carbon, the p orbitals, carbon, carbon double bond right here, and bonded to the X, right? The lone pair of electrons. Well, they're supposed to be the same size. I don't know why I drew it so large. I guess it's easier to see. But they'll delocalize. No, the p orbital of this X atom will overlap with the pi electron cloud of the CC double bond, and as a result, same thing. The partial double bond character bonds harder to break. As a result, there will be no reaction for this kind. So what you need to look out for is here. If the X is adjacent to the CC double bond, or if the X is adjacent to the benzene ring, like right here, adjacent to the benzene ring, adjacent to CC double bond. When this occurs, right, there will be no reaction because the bond is too hard to break. So that's the cases for the no reaction. And lastly, we will go through distinguishing tests. But before that, let me drink some water. Alright, drink some water. Distinguishing tests, well, there are two kinds. So the first one is the 4-step test, the second one is using ethanolic AgCl. So the 4-step test, right? If you have two compounds and you want to figure out which one is a halogen and derivative, right? Actually, wait. No, should we go through this first? No, I forgot to talk about the other reactions. My bad. Yeah, these kinds. Okay, so I guess I'll quickly go through this. So in summary, it can go through nucleophilic substitution reaction or elimination reaction. For nucleophilic substitution reaction, right, it can become an alcohol, a nitrile, an amine, or an ether. So for alcohol, this is the equation. For nitrile, this is the equation. But the thing is, for nitrile, right, when it becomes the RCN RCN compound, it can undergo reduction in two ways, or it can undergo hydrolysis in two ways. Now, the thing to note is that from the first way, right, the CC double bond will also be reduced because that's how it works. I don't know how to explain it. But for the second one, right, second way, right, the CC double bond will not be reduced. Only the CN bond will be reduced because the compound goes through the reduction via the H minus nucleophile. And since the CC double bond is electro-rich, the C minus nucleophile will not approach the double bond, so it will only reduce the CN. So besides reduction, the RCN can also undergo hydrolysis from this equation, Can also form an amine via this equation and an ether via this equation. So let me show you the more detailed notes. Go up. Oh wait, this is formation. Right. Formations of alcohols. Reagent is NaOH aqueous or KOH aqueous. Condition is heat or heat under reflux. And note that if ethanolic or alcoholic medium is used, elimination will take place. I forgot to talk about elimination. Yeah, elimination is just this thing. I guess I'll go through it later. For nitriles, it will be this, and the reagent is ethanolic or alcoholic KCN. Condition is heat or heat under reflux. And note that this is a step-up reaction. What this means is that it increases the carbon chain by 1 C atom. You see, right? This R originally has however many carbons in R, but after the reaction, it gained 1 more C. So, further reactions, for this reaction, this is the reagent and condition, and this reduces the C-C double bond as well. For the second reaction, equation is like this, and the reagent is this, and the Li AlH4, right, actually splits into the Li plus ion and the AlH4 minus ion, and the AlH4 minus ion further splits into the H minus, what's it called, nucleophile. So since it's negatively charged, it will not approach the double bond. So these are the two types of reduction you can remember. Then of course we have the hydrolysis of nitriles. These are the two equations, and this reaction, for this reaction, this is the reaction and condition, reagents and condition. For this reaction, it is this reagent and condition. So this is the acidic hydrolysis. This is the what's it called? Basic hydrolysis. The next step for nucleophilic substitutions, we have formation of primary amines. This is the equation. This is the reagents and condition. One thing to note is that for this, right, polysubstitution may occur. These are the equations. This is because, right, the this thing has a lone pair of electron on it, and we know that alkyl groups, right, this thing is electron donating, so it intensifies the, it makes this a stronger nucleophile because it intensifies the negative. It doesn't have a negative charge, but it's more negatively charged, I suppose. So this, right, would actually be a stronger nucleophile as compared to this, because if you remember, nucleophiles donate lone pairs, and this is more willing to donate a lone pair. So after you get this product, it will further react with the original halogen derivative to form this thing, and form. So polyalkylation occurs, and then you'll get, in the end, you'll get this product. And well, in the end, it will get this, but normally you get a mixture of all these 4 products. So what we will do is we'll use an excess of NH3 to minimize this from happening, because we know that this is a better nucleophile than this, right? So if we add a lot of NH3, then it will rarely react with this, and our main product will be this. And of course, we have our elimination reactions. Let me just draw this out, because what I wrote there isn't that accurate actually. Let's go back to this. So the elimination reaction, right? Elimination. You would have this, a halogen derivative, right? And then it would become okay. So let's see. So this is what is actually happening, right? These 2 adjacent ones, right? After reacting with OH minus, it forms a double bond, and the HX is eliminated. where the H goes to the OH to form H2O, and the X just remains as an ion. So that's what's actually happening. But if you look at what's going on here, it just means that the H and the X are adjacent each other, and when it reacts with the OH minus, it forms the alkene, the X minus ion, and water. So reagents and condition is ethanolic KOH or ethanolic NaOH, or ethanolic, same thing, whatever. Mix and match. You have four to choose from. Note that alcohol is used as compared to water, right? You notice they're not aqueous, they're alcohol. It's because OH in alcoholic media behaves better as a nucleophile. And we also have to note that the major product is the one with more alkyl groups attached to the CC carbons. I will probably explain this more in detail when I go through alkenes. But just keep this in mind, and remember that OH acts as a base in alcohol, but as a nucleophile in water. So if you notice just now, formation of alcohol, right? NaOH in water, right? It acts as a nucleophile to go through nucleophilic substitution to form this. But NaOH in alcohol or ethanol acts as a base, and as a result, it goes through an elimination reaction. So that's for that. And then oh yeah, preparation of phenol, no, benzene, halogenal benzene is this. I'll not go into it too much. And these are basically what I've explained just now, the case where for no reaction. Yes. Alright, then we finally move on to distinguishing tests. Well, the 4-step test, let me go. Oh yeah, this too, yeah, I think it's okay. Anyway, distinguishing tests, we have 2, as you can see. Let's see. First one is the 4-step test. Second one is ethanolic AgCl. So the 4-step test is this: heat your sample with Rx, with aqueous sodium hydroxide in a test tube. Step 2, cool the mixture. Step 3, acidify the mixture with dilute HNO3, which is nitric acid. And step 4, add aqueous silver nitrate into the reaction mixture. So, as we've explained just now, when you add aqueous sodium, I'm stretched. Yeah, aqueous sodium hydroxide to halogen derivative, nucleophilic substitution will occur, and the CX bond will break, and you will get the X minus aqueous ion. And the second step is to cool the mixture, because if you add silver nitrate in a hot mixture, right, AgNO3 will actually decompose to give you Ag2O, and we don't want that to happen because we want the Ag to react with our we want the Ag plus to react with our X minus ion. So we need to cool it, and step 3, we need to acidify it to remove any excess NaOH, because any excess NaOH will react with AgNO3 to form Ag2O. And note that we use nitric acid instead of hydrochloric acid or sulfuric acid, because the Ag plus ion will react. Ag plus ion from AgNO3 will react with the chloride ion to form silver chloride, and we don't want that to happen. So we want it to form. So we want it to react with the X minus ion. Same thing for SO4. The SO42 minus ion will react with this ion, and we don't want that to happen. So we can't use this 2 acid. We can use nitric acid. And then, of course, the last step, we add this to it to produce a precipitate of silver halide. And the color of the silver halide will help us to identify what X it is, what the X ion is, and then figure out what the Rx is initially. So same thing here. The first way, the first use of this distinguishing test is to distinguish between Rx. Because the different Rx, right? Let me find it. If the X is chlorine, right? A chloride ion, then it will be a white precipitate. If it's a bromide ion, it will be a pale cream precipitate. And if it's an iodide ion, it will be a yellow precipitate. So depending on the color of the precipitate, we can figure out the X. And the second one is to distinguish between Rx and pHx. Because as I've explained just now, right? pHx will not react, will not undergo nucleophilic substitution because of the strengthened CX bond. So if there's a precipitate, you know that it's the Rx. If there's no precipitate, you know that it's the pHx. pH stands for the phenyl group or the benzene ring. So it's basically an X attached to a benzene ring. Lastly, you can distinguish between Rx and other functional groups. So if there's a PPT, you know that it's an Rx. If there's no PPT, you know that there is no X functional group there. It's not Halogen derivative. And of course, our second test is using ethanolic silver chloride. So the chemical test is to add this thing to each sample. And for Rx, a white PPT will appear. But for ROX, there is no white PPT. And usually we use, well, this reaction is basically same as the fourth step, but it's simpler. So usually we use this in our theory paper, whereas when we write our distinguishing test, because it's easy to write, there's less steps involved. But in the practical, right, when we have to do the experiment ourselves to figure out whether it is a Halogen derivative, we have to use the first four-step test, because we have the reagents, all these reagents on our desk. But for this test, although it's simpler, we actually don't have ethanolic silver nitrate. So this is used for theory papers to write down because it's simple. And this is used for practical papers to do the test ourselves because it's possible, whereas this is impossible because we don't have the reagents. So it's basically the same thing, you know. This is what actually happens if you are curious. ALC stands for alcohol. And yeah, it's basically that. So that's the two main tests we use. So this is for the fourth step, the two tests, and which two cases we use them and how we can use them to distinguish them. So okay, two tests. You need to know when you use it, and you need to know how you use it. If you're distinguishing between Rx's, distinguishing between Rx and pHx, or distinguishing between Rx and other functional groups. And then that's pretty much it. The rest, right, is, you know, the use of this thing and this thing, but you can just read your own notes. I don't really want to go through the entire thing. It's quite tedious, so just memorize some stuff from here. They will test it, but it's not that, I don't think it's that extensive, so you know, just read a little bit. I'm pretty sure it's quite easy to remember. It's a little bit of common sense and chemical intuition mixed into it. So this will do it for our halogen derivative halogen derivative revision. Yep. And do I have anything else to say? Probably not, but this was fun. Was it fun? It was somewhat fun. I had good revision, but my throat is actually not doing that well right now because I've been talking for too long. But the good news is I'm gonna have pizza for dinner later, so I'm looking forward to that. And yeah, that was quite the revision, isn't it? Well, I hope it has been helpful for you guys. Let's take off our Megane blue. Hey, what up? Anyway, this is the end of our halogen derivative revision. I hope it has helped. Oh yeah, I wanna tell you guys. Besides chemistry, I also study economics, physics, and math. So I might do some revision or guide for those as well. Actually, wait. I also have some questions, right? Okay, so can go through some questions. Well, I guess I don't have time. Yeah, maybe I'll go through the questions next time if I have the time to do so. But this will do it for halogen derivative revision. Yeah, let's look at YouTube. Yep. So this is the end. I've said this so many times, right? I really don't know how to end something like this. Well, yeah, I hope you guys had fun learning. Oh, see you later, alligators. Bye bye.